Thank you for being here.
Thank you, Karen. Thank you all for being here too. This is an adaptation of my exit seminar. I have some new results and a little bit of more information. So the title is from my dissertation, as Carol mentioned. Farah Carrasco Rueda and Betty Leisel has been my advisor during these 5.5 years. So I wanted to start talking about a little bit about bats. Why bats? Why using bats as a study? They have different characteristics that make them great organisms for study. So here you can see that they have extremes in size. So the small species like this Micronectaris minuta, really small, at least in Peru, one of the smallest. And this is a species that is the largest for the neotropics, I guess, and for the country of Peru, Bolivia, and Ecuador. So variability in their morphology and also in their habits. Most important maybe is that they provide several ecosystem services, or they have different functions in the ecosystem. For example, these species are Insectivores because they have this adaptation of a long phase to reach into the nectar part of the flowers. They feed on nectar and they are helping us pollinating plants. But also we have other group of bats that feed on fruits, and they're called Frugivores, and they are helping us dispersing the seeds. So here are some examples of some seeds that one of my volunteers found in the feces from the bats that we captured. So different species of plants can be dispersed by this group of animals. But also we have this important group that are the Insectivores. Why? Because they are collaborating with agricultural activities by the control of pests or insects. And our group are the carnivores. Some feed on amphibians, some on fish. So carnivores feed on other bats, small rodents. And they are also kind of helping us controlling these populations of animals. And this group is not actually giving us a service, but they feed on blood. So we have, for example, for Peru, we have around 180 species of bats, different gills, profit gills, as I was told. But only 3 of them are sanguineous. 2 of the 3 feeds on the blood of birds, and only 1, the smallest rotundus, feeds on blood of mammals, cows, tapirs, peccaries, and also humans. And here is a picture that I wanted to show. You can notice who is in here. It's a tapir that is, and this is a picture from the lower Urubamba region. And if you notice already, this little guy is on his back and is feeding on him. This is the first day or first night of a series of 3 days. And I guess, or I think, almost sure it was the same individual tapir that was being attacked by this vampire bat. So to continue with the characteristic that makes bats as a great study group is that they are actually susceptible to this kind of human perturbation. And this is important because in countries as Peru and other Latin American countries, we are having a great rate of deforestation because of land use change. So we are having really bad forest loss in general in different parts, especially in the Amazonian forest. Hopefully, more thankfully, our government, Peruvian government, has established some measures to mitigate these activities. And one of them is the maintenance of these riparian forest strips. So as part of the Peruvian law, we have the law 29338, is the Hydric Resources Law, and they define these fajas marginales, or riparian forest strips, as the immediate areas above the riverside or the stream banks that are of public domain for hydraulic goods. So everybody can go into this riparian strip because it's the government or the national property. And they establish some criteria to define how wide this riparian forest strip should be. And the first one is that they should provide enough space for constructing or for the conservation or protection of the riverside defense or the riverbed. And also they should consider the maximum level of water when there is a high in the rainy season, the water of the streams go really high. And also they should provide enough space for required public use. For example, fishermen are using the stream, so these areas should provide enough space for them to walk on the side of the stream first. Unfortunately, or maybe it's something good, the law is not defining the width of the riparian forest strips. And they established that this is the water administrative authority, the one that should determine the width of the streams depending on or following the criteria that is established in the regulation. So this is an example for the San Martin region, where they are suggesting this width for this kind of stream. So a stream with less than 5 meters wide should be 2 meters of riparian forest to each of the sides. And the other extreme is for streams that have less than, more than 10 meters and less than 50 meters. They should have only 10 meters of forest or riparian forest to each side. So this is what they should suggest. But the owners of the land can decide, actually, with the advice of these organizations, how wide they can be, the riparian forest strip. So in this context, I was wondering if these riparian strips have conservation value, if they help to maintain the biodiversity in this area. So imagine that you have a continuous forest and it's full of bats flying everywhere. And then a company buys the land, that is what happened, and they decide to clear the forest to establish a palm plantation. So they clear the forest, but they keep this riparian forest strip because it's by the law, they should keep it. And with some advice of different specialists, they decide to keep just 25 meters to each of the sides. That is much more, or kind of more, than the number that the regional organization was suggesting. So this part of the dissertation was undertaken in San Martin, that is in the central Amazonian forest of Peru. And as you can see in this map, that is from 2017, it's showing a lot of yellow and red. That is because the region has a high deforestation rates in that part of the country. And I was there working between May and July 2014. And this is a satellite image from 2013 of how the land that the company bought looks like. It has some areas that were already intervened. And in 2014, they did the clearing. I didn't find any image for that year, but this is how the land ended up. So you can detect here these green lines that correspond to the riparian forest strip that were surrounding both streams that run along their property. So, and they use this kind of machinery. Actually, we're moving these machines to go into the sampling sites. And this is how the land looked after they cleared the area. They didn't clean. So it's not like, I call it clear area, but it's not clear because all the trees were fallen in there. So I wonder if this strip has some conservation value for biodiversity. And actually, I had the chance to go there thanks to TCD and Tinker research grant. So this is the design just to play, and I need to put a little bit of attention because it can be really confusing. I established 3 different treatments. The first one was continuous forest in here. It didn't have the presence of any water source, no streams in there. Second treatment, we have again the continuous forest, but with some stream running over there in the circles. And then the last one was the area already intervened by the company. They cleared the forest, but they kept the riparian forest strip of 25 meters to each side of the streams. And it's here in this part. And for these 2 sites, A was a really recently cleared area. It was like 2 weeks before I went there to sample. It was really bad. And the other side was actually a site that has at least 2 months after the clearing. So it was a more, it was like kind of reaching the equilibrium after the clearing activity. And this is how it looked again. So the forest, I defined 3 different habitats. It was the stream that was over here. I couldn't take a picture. The forest and the forest edge that was really sharp, and this was the clear cut area, the clear area. And I replicate the sampling design in all the treatments. I have in these red dots, I have a pair of nets in that position, like an L shape. So I have 2 locations with nets close to the stream, 2 at the edge, 25 meters away, and 100 meters away, another pair of nets. And I did the same in the areas that the clearing wasn't there yet. So it was here in the previous treatment was clear area, and here was continuous forest. And I had also the streams in this treatment. And in the last treatment, I didn't have a stream, but I just put the same design. I replicate. And so we capture bats during several nights between 6 p.m. to midnight. And at the end, we worked during 48 nights, and we captured 1,200 individuals that belong to 48 species from 5 different families. But you can see here that the green one that corresponds to the Philostomidae was the most abundant because mist nets are really effective to capture this kind of species, not the other species that belong to the other families. So the analysis I will show is focused in these 43 species of Philostomids, and they belong to 8 different trophic eels. We had the Carnivores, Frugivores, Insectivores, Carnivores, Omnivores. So just to show you that pulling together the data from the different habitats, but making the difference among sites, we didn't find any difference among the treatments in terms of their species composition. However, when we took a look into the habitats and their capture rate, so just to make clear that here is the species rank refers to the position of each of the species captured in each treatment. And the species that is in position 1 is the one that has the highest capture rate for each of the treatments. So you can see here that the darkest line corresponds to the forest without stream, and they had, in general, lower capture rate compared to the areas that have a stream, meaning with the clear area or with the continuous forest. So you see that in the case of riparian forest strip with the clear area, there is few species with really high capture rates, more like common species, and a tail, this representing several rare or rarely captured species. And here I'm dividing information by habitat. So you see that in this treatment that has a stream with the forest, the capture rate in the streams and in the forest habitat didn't differ much in the shape of the curves. But if you see in here in this treatment with the riparian forest strips surrounded by a clear area, the stream and the edge habitat that is in here and in here had this shape of the curve with few species with high captures and really a lot of species with really low capture rate. And this is just looking at how the assemblages in each of the treatments separate among them, how the composition of the species in each of these groups of samples are similar or different among them. So you see that here F1 and F2 correspond to the forest, continuous forest without the stream. They are separated in this ordination space from the other two treatments. Both of them have the stream in the tree. And this is more detailed. So if I separate the information in terms of the habitats, the axis is separating the information in terms of like a gradient of perturbance or disturbance. You have on the left all the transects that are pure forests. At the middle, the ones that correspond to the riparian forest strip, and on the right, the ones that correspond to the clear area. And all this was talking about species, number, and capture rate. But what happened with the functionality, with the number of trophic yields, the presence of nectarivores, omnivores, carnivores? So if we take a look to the treatments, we see that there is not much difference in the presence or absence of trophic yields among the treatments. And if we see specifically to the riparian forest strips surrounded by clear area, in the site that was recently cleared, the trophic yields are maintained. However, in the site that was a little bit old in terms of the clearing time, we see that in the clear area where the forest was taken down, we only found 4 of the trophic yields, compared to 6 or 6 in here, in the matrix of the recently cleared area. So, some of the conclusions for this part, we see that the riparian forest strips are showing high capture rates and high species richness, and they are maintaining the trophic yields in general, the diversity of trophic yields. And however, also I detected that there are some perturbation-sensitive species that were absent in the riparian forest strip compared to what we found in the forest treatment. So we can say that actually this riparian forest strip if we take a look into the recent stage after the clearing, they are showing a conservation value because they are maintaining 80% of the species that were registered as forest. 80% of those species that were registered when there wasn't any human intervention were present in the riparian forest. But I am highlighting this part because I didn't have the chance to come back and to do the same sampling a time after the clearing, that the situation can change drastically. So, and now let's change a little bit of context. Let's think about what happened when we have a continuous forest that is adjacent to an area that was cleared for agricultural land. And in this area, we have two different types of agriculture activity, or papaya plantation or cattle pasture. I wanted to know what happened, how this presence of our agricultural land is affecting the bats in the forest, and also what is maintained in this area that is already with that anthropogenic activity. So for this part of the thesis, I went down to Peru into Madre de Dios region, that is in the southeast part of the country. It is considered as the capital of biodiversity by our government. And we went there during 3 visits, 2 in 2016 and 1 in 2017. And as I mentioned before, we focus in 2 different agricultural lands, the papaya plantations that started as a boom of an agricultural activity since 2013, and the cattle pasture that, on the other hand, is like an old activity and has been encouraged by the government since the 1970s. So I have 3 objectives for this part. First, to describe what was happening there. Is the agricultural land type influencing the forest bats, how the diversity is in the forest actually? And once I see what is the pattern, I wanted to understand a little bit more about the underlying mechanism. And last, I will know what happens in the forest, but I also wanted to know what was maintained in the area that was affected by agriculture. So in this case, I have this beautiful design with 3 different habitats again: forest interior, forest edge, and the agricultural land that could be papaya plantation or cattle pasture. And I replicated this sampling design in 12 sites. 6 of them have papaya plantations, and 6 of them have the cattle pasture. And again, we went there with our mist nets, and we were working in the same period between 5:30 p.m. to midnight, and we were capturing the bats. We are really covered because there is leishmania and we didn't want to. So we worked during 87 nights, and we captured 3,600 individuals. Again, the most part of the species belong to the Philostomidae family. And in total, we have 56 species, but only 43 are philostomids, and they belong to 8 tropicales. So first, when we examine the patterns of, or how the agricultural land is impacting the philostomid bats in the forest. So here I'm comparing, as you can see, what is the species richness in the forest and at the forest edge, and here the capture rate at the forest interior and the forest edge. And only we found that there is a treatment effect in the species richness, with the papaya plantation showing the highest species richness compared to what we found in the cattle pasture. And again, this is the separation or the ordination separating the assemblages that we found in each of the habitats. And you can see that they are grouping by habitats and not by treatment. So we have forest, and it didn't matter if it was forest adjacent to the papaya or adjacent to the cattle pasture. In the middle, we have the edge habitat, and on the right side, we have the production land. So if we overlap, sorry. This is how the assemblages were separated, exactly how the landscape looked. Forest interior, forest edge, and the production. And habitat is driving this difference in the assembly. So some conclusions, as I mentioned, the treatment is having an effect on the species diversity and also in the trophic yield richness, with higher levels in papaya plantation sites. And the habitat is driving the composition of the species composition. And the forest interior are showing higher total species and some trophic yields captured. So for the second part, that is a little bit more dense and complicated, we try to understand the mechanism that were behind these patterns. And for that, we did a lot of measurements for different factors we consider might be influencing the patterns. So we did some measurements at the landscape scale and some measurements at the local scale. So for the local scale, we measure vegetation structure. And for that, we did some measurements of the horizontal density of the vegetation using some pictures converted into white and black. And in this kind of picture, we measure the amount of black color as an indicator of the density of the vegetation, for example. Here are my volunteers measuring the density of small trees. We also measure the density of big trees. We had a profile of the vertical density of the vegetation in each of our habitats in forest and forest interior, forest edge. And we also measure the canopy height in each of the sites. In addition, we had these data loggers taking data from the temperature from each of the habitats. And for the landscape scale, we use this satellite image and NDVI information to estimate how much forest cover, percentage of forest area or forest cover were surrounding each of my sampling sites. And we use different radius for that, or buffer areas, from 400 meters to 5 kilometers. And this is a summary showing that for most of my response variables that include species richness, capture rate, and the capture rate for different trophic yields, a combination of several of the local scale factors are important to explain the response variable. On the other hand, in the landscape scale, we have some positive and negative effects depending on the type of variable we were measuring. So for example, for the capture rate of gleaning insectivores, the amount of forest cover at 5 kilometers radius was important for explaining the response variable. So some conclusions for this second objective: the local predictors are explaining taxonomic diversity, the overall capture rate, and also capture rate for some of the trophic yields. And in the case of the landscape scale, some forest cover buffers are explaining or positively associated with the trophic yield richness in general, and also with the capture rate of almost all the. And for the last part that I wanted to, we already see here what was happening with the bats in forest habitat, but we didn't mention actually what was happening in the agricultural land itself. So in here, we're going to explain a little bit of that. So this is an image that is similar to a puzzle. In each of is separated among habitats, and if you focus, for example, in their position, this is Artibeus obscurus. And it was present in the forest, in the edge, in the papaya habitat, but it was absent in the cattle pasture. So if you follow that logic, you will see that also is divided by type of trophic yields. So frugivores, nectarivores, omnivores, insectivores, carnivores, and sanguivores. So between edge and forest interior, there are most of the species are shared, and also a couple of them are present in the forest interior and access in the forest edge, and vice versa. But in the case of papaya, you can see that there is less species present, and even in cattle pasture is much less species present. And actually, gleaning insectivores, carnivores, and sanguivores, they are absent in cattle pasture. And you will wonder why sanguivores. Okay, so my misses were located actually far away from the area where the cattle was speaking, because they were really problematic. They were taking down the business. So we intentionally try to get them far away, or we place the niche nets with carefully separating them from the cattle. And I assume that if the vampire bats were around, they will be more interested to be close to the cattle than close to the forest edge, or in the pasture itself. So we might say that papaya plantation, if you compare cattle pasture with papaya, is working better in terms of harboring more species and more phytostomic diversity. And actually, we noticed something in the field, that these are frugivore species from phytostomic bats might be providing some services for papaya producers. Why? Papaya producers are not selling the fruits as this. They are selling the green, the unripe fruit. So they don't care. They don't pay attention to the ripe fruit. Just biology. We're eating papaya all day. But so bats and other mammals were feeding a lot of these ripe fruits, and actually that might be helping the tree to keep some energy and not investing it in providing some energy, or I don't know what exactly, to the papaya that is ripe, and that energy can be invested in the ripe. And this last part is just to show you that if you notice, our misnets were not higher than 3 meters, so we were able to capture all the bats that were flying in the understory. But what happened with this bat? With the other group of bats that fly above the canopy and in the open space. So for those species, we use acoustic monitoring. And also we were aware that they have different echolocation called shapes. So the species that are flying in open space, they have kind of flat shaped echolocation calls that allows them to reach really far distance for detecting the insects that are flying in the open area. And it's different from what you can see in the echolocation call from species that fly in the edges, that have a combination of flat parts and then really, how do you call that, steep calls. And that's also different from the ones that are flying inside the forest that have this kind of shape for the calls, because they need to be able to detect obstacles all the time, like the obstacles that are really close to them. So knowing this, that this, depending on the space that they use, their echolocation calls can be different. We were wondering how different habitats maintain diversity of this aerial insectivore group of species in the Madredios, in the same system that we use for studying the phyllostom tags. So this time we didn't use the misnets. We used these two types of bat recorders that are able to detect high frequency calls. And we place them again in the 3 different habitats, for interior, edge, and the agricultural land. And as a result of the analysis I did for the dissertation, we worked with more than 200 hours of sampling, and that resulted in 14,000 recording files, and those have 5,800 occurrences. That means that one bat was detected in 1 minute period in the recording files. So I can have I can detect the species several times in like 3 files, but if those 3 files were in a period of 1 minute, it represented only one. So we end up having 25 zone species. And why zone species? We weren't able to identify some of the bat echolocation calls into a species level because they are unknown actually for Peru and for several of the tropical countries in Latin America. But because of the characteristic of the shape, we knew which family they belong to. And they belong to 4 families and only 2 trophic yields, the background and clutter space aerial insectivores that are also known as edge space species, and the uncluttered space aerial insectivores that are known as the open space. And these are some examples of the program I'm using to analyze the acoustic data. So this is 3 different species from 3 different families. Emballonuridae, Vespertilionidae, which I couldn't identify the species exactly, and Nautilio oliventris, who is an insectivore that feeds on above the water surface. So you can see that these actually beautiful shapes for each of the species, and this is helpful because at the beginning it's just lines, right? But after several hours of looking at these different files, you get the patterns and you remember them. So it's almost automatic. This video. So you remember I had 14,000 files with recording. So it was a crazy amount of information. And what I decided to do first is, without putting any ID in the recording files, I put all the data, all the files into the program. And I asked the program to extract the characteristic frequency present in each of the files. So in that way, I can estimate how dense or how many calls or pulses had each of the frequencies in them. So you see that in forest, this is papaya plantation sites that have forest edge and the papaya itself, and the same for cattle pasture, forest edge and the cattle pasture. In this agricultural land, the range of characteristic frequencies is wider compared to what we found at the edge and at the forest. Same for papaya and pasture. And I use a diversity index using each of the characteristic frequencies simulating a species to calculate how diverse in terms of characteristic frequencies each of these habitats were. And cattle pasture ended up being the most diverse habitat. And this might be reflecting that it's actually more a higher amount of families present for bats or also species. But this is not including any ID, just looking at the diversity of characteristic frequency. After I identify all the species, I could do this. I had the chance to do this kind of analysis using this activity index that is simulating or approaching relative abundance, but using the occurrence of the bat species in the recording files. And we can see that there is an effect of a habitat when we are comparing forest interior, edge, and matrix, with forest habitat showing the lowest activity index for the area insectivores. And as I mentioned, we only registered two different trophic yields, the edge species and the open space species. The edge species didn't show any significant statistically different differences, but the open space species, they did, and again, they had really low activity index inside the forest habitat. And here I'm separating the different habitats, again, but showing kind of a parallel to the accumulation, branch accumulation curves. No, branch abundance curve, but it's using activity index. Again, the first, the number one is showing the position for the species that had the highest activity index. And you see that the curve that is in blue that correspond to forest interior is really flat because it's almost all the species present in the forest habitat were really low in their activity index compared to what we saw in the edge papaya and pasture that have similar shape of the curve, with some species presenting high activity index and much more numerous species with really low activity index. And in terms of the assemblages, the forest interior was really different from what we found in the other three habitats, in edge, in papaya, and in cattle pasture. And that might be showing that these three habitats are providing similar resources to their insects compared to what is happening in the forest. So for this part of this dissertation, we can say that agricultural habitats, papaya and cattle pasture, are showing a broader range of call frequencies compared to the forest interior and the forest edge, and that may be reflecting a higher diversity in terms of aerial insectivores. And contrary to what we expected, the forest habitat had lowest species richness and also the lowest activity index. And we did not find any difference among the habitats in edge, cattle pasture, and papaya. So some take-home messages from the whole dissertation is that first, if we go back to the riparian forest strip, they actually constitute an effective tool for maintaining the diversity and as a mitigation way to reduce the impacts of agricultural activity in early stage of the clearing process. And the agricultural use is maintaining a subset of the philostomic bats that were originally in the area, but we compare with the forest bats. And also they are showing a high activity of aerial insectivores. And finally, that this study with the aerial insectivores is like a first step for quantifying the pest control service that are providing bats for the agricultural activities. So, because PCD provided me a practitioner grant for this year, I went back to Peru in August and September, and I visited several elementary schools using these bat cartoons as a communication tool And it was really, really useful. Kids pay a lot of attention when they see kind of cartoons. And I also previously went back to the owners that provide me their permission to go into their land, and I gave them this poster with information about several of the species that I registered in their land, trying to change a little bit their perception about bats, because they were like, oh, they're ugly, you kill them all. But no, they're actually helping them in some ways, and this was a way to provide information. And here are some pictures from the dogs I provide to elementary schools, the rural schools in close to the highway in Madre de Dios, the Interoceanic Highway. And those are some examples of the dogs. And it was really, really nice experience. It's also intense talking to kids. But as I told you, working with cartoons, I found it really useful in general. So I wanted to thank all my funding sources, all my field assistants and volunteers that helped me during the fieldwork, always. And Betty, thank you so much for receiving me as a student. This has been really, really great 5.5 years. And thank you for my lab mates, friends here. And thank you for paying attention.